All right. Good afternoon, everybody. Let's go ahead and get started. Thank you so much for your time, and hopefully everybody's having a great re:Invent so far. My name is Chetan Kapoor. I'm part of the EC2 leadership team, and I'm responsible for our hardware accelerated business. And I'm going to be co-presenting this session with Ron Diamant, who is a senior principal engineer with our Annapurna team and is the lead architect for our custom deep learning silicon. So today in this session, we're really excited to talk to you guys about our latest TRN1 instances and the Trainium chip that we have built, which we believe will provide the lowest cost to train some of the most cutting edge deep learning models in the cloud. So over the last few years, we have really seen AI ML take off with a whole bunch of use cases and applications coming to bear. So machine learning has gone from a technology that was mostly limited to like large tech companies and hardcore academic researchers to now at a point where we're seeing large enterprises to startups using machine learning and AI ML to reinvent their businesses and provide a lot of value to their customers and also their stakeholders. We are seeing machine learning across a whole range of workloads and customer segments. In fact, we have over 10,000 customers that are building, tuning, and deploying machine learning applications on the AWS cloud. As a matter of fact, we believe more machine learning applications are built and deployed on AWS than any other platform out there. As a few data points, Pinterest uses AI ML capabilities for object recommendation, object detection, recommendation engines. We have customers like Uber and Lyft who are using machine learning for route planning activities and lots of other really cool use cases. Over the last few years, as more and more customers have started to use machine learning, we're observing a few key trends on the infrastructure side. We are seeing customers move from using classical machine learning techniques to now using deep learning techniques. And on top of that, the size of the models that they're building is growing exponentially. So with this complexity and growth in the size of the model, customers are aiming for achieving higher accuracy for their predictions, and they're also looking for delivering more personalized experience for their customers. As a direct consequence of this complexity on the model size, we're seeing that customers are telling us that the time and the cost to train these models is also growing exponentially, right? Specifically on the time to train, models have gone from being trained in a few hours, now again back to like needing weeks and sometimes even months of compute to actually achieve the required accuracy for a certain model type. Along with this complexity is the fact that machine learning engineers and data scientists want to iterate really quickly on their designs and models, right? So it's really limiting if it takes a really long amount of time and costs a lot of money for somebody to train a model, and they're unable to iterate really quickly on it to optimize it, refine it for their use case, and ultimately deploy it in production. So besides training these complex deep learning models, we're seeing similar challenges on the inference side, because once you have a trained machine learning model and you want to run it against production, that's where many of our customers also tell us that there's a lot of cost involved in running these really complex models at scale. And lastly, what we're also hearing from customers is that they love the fact that AWS and the other providers are kind of innovating quickly on the hardware and the infrastructure side. What they're also requesting is a software experience where they're able to maintain or exercise the knowledge and know-how that they have, but at the same time have the ability to take advantage of these cutting-edge products that we are building. So again, to summarize, customers are telling us it takes too long, costs too much to train these models, and oh, by the way, I would love to make sure that you guys are providing us a solution where I can continue to be effective and productive and not have to relearn new sets of tools, capabilities in order to leverage the new hardware innovation. So on our side, we have been focusing throughout what we call as the AI/ML infrastructure stack and innovating across the spectrum. At the bottom layer, you guys see that we're going to continue to partner with our key silicon providers such as NVIDIA, AMD, and Intel to provide you access to their cutting-edge silicon in form of instances as quickly as possible. In parallel, we're also investing in building our silicon, which is specifically the Trainium chip that we're going to talk about, and the Inferentia chip was the first chip that we launched about 2 years ago. At the server level, we're also innovating at that stage. We have talked in some of our previous talks where the Nitro system that AWS has, we're building our own storage cards, we're building our own network accelerators that allows us to innovate quickly and also provide differentiated experience from a software and a hardware perspective. As you will see with Trainium, we have packed 16 Trainium accelerators in a single instance. That packs in a lot of power in a single server. And besides the compute, again, we're pushing the boundaries on the networking side also. With TRN1 instances, we're going to have 800 gigabits per second of network throughput with roadmaps to actually go beyond that also. Besides innovating at the server level, we're also taking it a step further and innovating at the data center level, where we introduced a capability called Ultra Clusters, which are densely packed, co-located racks of compute, all interconnected via a non-blocking petabit scale networking, and supporting an MPI-style network interface, giving our customers the ability to spin up not only just 1, 2, but hundreds of these machines to run in parallel to really cut down the time to take these, train these complex deep learning models. And lastly, in order to make sure that it's, all this infrastructure innovation is easy to use by our customers, all this capability is going to be integrated in our managed services such as SageMaker, which provides the end-to-end framework for building, training, and deploying machine learning models, along with support for containerized platforms such as ECS, EKS, for managed experience. Ron is going to talk a little bit about it, but on the software side, we have a very, very sharp focus on making sure we provide a seamless experience for our customers that builds on frameworks such as TensorFlow and PyTorch. We're seeing a really great adoption for PyTorch recently, and the Neuron compiler that we're building that supports the Trainium accelerator is going to be integrated under PyTorch to make sure customers have a really seamless experience to take their existing models and start training with the Trainium accelerator and TR1 instances. So from a portfolio perspective, just a quick run through of what we have in the portfolio today. We were first to market with general availability of A100-based instances last year. Earlier this year, we announced our DL1 instances featuring accelerators from Intel Habana. And on the inferencing side, we have a range of offerings there to help you right-size your inference requirements. So we have our G4DN instances featuring NVIDIA T4, the latest G5 instances that we launched about a month ago, featuring the NVIDIA A10G. And then we have our Inf1 instance we launched almost about 2 years ago, featuring up to 16 Inf1 accelerators, Inferentia accelerators for running deep learning models in production. And today, as part of this talk, we're going to be focusing and diving deep on the TRN1 instance and their features and capabilities. So let's take a closer look. So we believe TRN1 instances will provide the most cost-effective platform for training deep learning models. The image over here shows a part of the server that supports the TRN1 instances in the back end. In this picture, you guys can see there are 8 accelerators that are populated, and you have power and other cooling subsystems there. The math engine on a Trainium accelerator runs at about 3 gigahertz. At the server level, we've packed in a total of 3.4 petaflops of TF32 and bfloat 16 performance. Native FP32, we have 840 teraflops. Again, at the server level, the aggregate accelerated memory is 512 gigabytes, peak memory being a little over 13 terabytes per second. All of these Trainium accelerators in a single instance are connected to each other using what we call as Neuron Link. And on a per chip basis, we support 768 gigabytes per second of point-to-point communication to support operations such as alt-reduce. And for the external connectivity from the instance, as I mentioned earlier, this particular platform has 800 gigabits per second, which is the first time we're introducing this capability in EC2. So let's take a closer look at the actual instance sizes. So we'll have 2 instance sizes available with TRN1 2XL being the entry size that comes with a single Trainium accelerator, 8 vCPUs and 32 gigabytes of system memory to go along with it. And we'll have up to 10 gigabits of networking connectivity. The largest size is when you have access to the full resources in the server platform with 16 Trainium accelerators, 768 gigabytes per second of Neuron Link that has been activated, 800 gigabits of networking connectivity, 8 terabytes of local NVMe storage. And all put together, this platform provides 60% higher accelerator memory than our current GPU instance, 2x higher networking bandwidth than, again, our latest generation GPU instance. I already talked about the native integration with PyTorch and TensorFlow. And when you train using TRN1 instances, the train model, you'll have the ability to deploy that anywhere. This could be on GPUs, CPUs, Inferentia, or even an edge platform if that is the preferred deployment target. These instances are in preview today and will be generally available in the first half of next year. Okay, so I talked a little bit about Ultra clusters. Let me spend a couple of minutes on it. So Ultra cluster is considered as a really large cluster placement group where we have co-located racks and racks of TRN1 instances in a specialized data center. So in this case, we're going to allow our customers to spin up, a cluster that can consume up to 10,000 Trainium accelerators as part of a single cluster run. So all these racks of TRN1 instances are co-located. They're all interconnected using petabit scale non-blocking network infrastructure, and also have storage platforms co-located for you to spin up FSX for Lustre type of network attached storage services to make sure you have a really high throughput storage platform to keep your cluster busy and operating efficiently. Looking at the total compute available in a cluster this size, again, just doing the math on how many petaflops we have on a per server basis, we believe we'll be able to provide up to 2.1 exaflops of compute in a single cluster, which we believe is at the same levels of what you typically see as a supercomputer, but available on a pay-as-you-go usage model on AWS. Great. So outside of the server platform and the instances, these are going to be integrated with the entire suite of AWS offerings. So we have support for EFA, for low latency network communication, access to S3, EBS, FSX, and EFS for storage options, and also other high-level managed services like I mentioned earlier, SageMaker, Deep Learning AMIs, ECS, EKS, and integration under PyTorch and TensorFlow. Now, from a customer use cases perspective, we have a customer called Anthropic. They're building some of the most complex deep learning models that the community has seen, and they're super excited about being able to leverage what they call as the unprecedented capability that Trainium-based Ultra clusters will provide and help them bring their innovative products to market. Sprinklr is currently building natural language processing models along with computer vision models. They have currently deployed these models on our Inferentia-based platform for running their models in production, and they're super interested and keen to look at using Trainium to help lower the cost to train and obviously speed up their innovation cycle. With that, I'm going to hand it over to Ron to go through the Trainium accelerator architectures and the innovative things we're bringing at the chip level. Ron?
All right, thanks, Chetan, very much. Folks, thanks again for joining us today. My name is Ron. I'm part of the Annapurna Labs team, which is the silicon team within AWS. And I lead the architecture team for deep learning accelerators, Inferentia and Trainium. I'm super happy to be here with you today to talk about the Trainium architecture and how we designed it to deliver the best price performance for machine learning training. Let's dive right in. Here's a quick overview of the Trainium architecture. Each training device has 2 neuron cores, HBM2E memories, and dedicated collective compute engines, which allow us to overlap between computation and communication during scale-out training. And we'll talk about that more. Each neuron core has a tensor engine, a scalar engine, and a vector engine. The tensor engine is optimized for matrix operations, like matrix multiplication and convolution. The scalar engine is optimized for element-wise operations, which means that each element in the result is dependent on one element in the input. Examples for these operations are ReLU and exponent. And the vector engine is optimized for non-element-wise vector operations. So these are situations where one element in the result is dependent on multiple elements in the input. And a few examples here are pooling operations and batch normalization. We also have deeply embedded general-purpose DSPs inside the neuron cores, which are tightly integrated with the other engines. And this allows our customers to implement their own custom operators in straight-line C++ code and run them on the neuron cores. And this prevents needing to move data back and forth between the device and the host. Our customers use a variety of data types in order to optimize for training accuracy and speed. And TRN1 is the fastest instance that we have across data types. Relative to P4D, TRN1 delivers 1.4x the bfloat 16 teraflops, over 2.5x the TensorFloat 32 teraflops, and over 5x the single precision, or floating point 32 teraflops. TRN1 also introduces a new data type called configurable float 8. Float 8 is an 8-bit floating point data type, and it provide a couple of advantages, like compressed model size or reduced I/O bandwidth when we do distributed training. And configurable float 8 means that our customers can trade off between the range and precision during float 8 calculations on a per operator basis. And this was shown to improve accuracy for float 8 training. Here on the slide, you can see 3 configurations of configurable float 8 with different bits allocated to the range and the precision of the data type. Different number of bits. We also baked a new rounding mode into Trainium called stochastic rounding. And customers can choose between using the standard round nearest even rounding mode or this new stochastic rounding mode. And to understand why stochastic rounding can be useful, let's examine one of the most common calculations that we do during machine learning training. We take a weight value and add a small weight update to it. And with round nearest even, if the weight update is small enough, it can be completely squashed by the rounding operation. Let's get some intuition. Let's look at an example. Let's say that we add 2 numbers together, 1 and 0.2, and then we round the result to the nearest integer. The result is going to be 1, right? Even if I add 0.2 to 1 5 times in a row and do a rounding operation after each addition, the result is still going to be 1. Now you can intuitively feel that something is off here, right? With stochastic rounding, this problem is resolved. What we do here is that every time we round, we do it stochastically according to the relative distance from the 2 closest representable values. So back to our previous example, we had 1 and 0.2, and add and round it to the closest integer, but this time we use stochastic rounding for that. So now the result is 80% chance of being 1 and 20% chance of being 2. And over large computations, this tends to average out and produce with more accurate results. There's actually a lot of work out there that shows that stochastic rounding produces overall better accuracy when training models, and especially when using low precision training like float8. Here, for example, I copied one work that showed the differences in stochastic rounding and round nearest even for low precision training. So what this graph shows, and let's focus on the graph on the right, this shows the test error for a model that we're training, and it shows that for a variety of data types and rounding modes. The black line is the baseline. Here we train the model with FP32, or single precision data type. Then the yellow and green lines are training in low precision. This one is not float8, it's another data type, but there are similar works for float8. So we're training at low precision and with round nearest even. And you can clearly see that the error is higher than what we got in the baseline. And then the blue and red line that look very close to the black line are the same exact low precision training data types, but this time with stochastic rounding. And you can see how you get much better accuracy or lower error. But one call out that we keep hearing from scientists that are using stochastic rounding for doing these experiments is that they currently need to emulate stochastic rounding because it's not supported by the underlying hardware that they run on. So in Trainium, we implemented stochastic rounding natively in hardware and without any performance overhead. We get the same performance with round nearest even or stochastic rounding. And we're super excited to see what the community is able to achieve with this new capability. For many of today's deep learning models, we cannot think of one device anymore. Training is no longer a single device workload, and we have to think about scale-up. Over the last couple of years, we saw more than 10x per year growth in model sizes, especially in the natural language processing domain, but in other models as well. And the computational demand for training these models also grew at a similar pace. The reason that models are growing so rapidly is that the larger models are producing more accurate results. And this could lead to a more meaningful answer from Alexa, or a better movie recommendation, or any other advantage in these lines. And while the results that are achieved by these large models are super exciting, we also see a problem with this trend. Because you see, servers are not sped up by 10x every year. So there's a growing gap between the computational demand to train a deep learning model and the computational speed delivered by a single server. And to address this gap, machine learning practitioners are using distributed training techniques. That's where you use multiple devices and sometimes multiple servers in order to do a single training task and complete it faster. So we knew that we need to make sure that Trainium and TRN1 are optimized for scale-out from day one. There are a couple of different ways to do distributed training or scale-out training, with the first and probably the most intuitive one being data parallelism. With data parallelism, we hold a full copy of the deep learning model on each one of the workers. And then we take the training data set and split it between the different workers. At this stage, each worker processes a set or a batch of examples, which we typically refer to as a mini batch, and computes parameter updates, which we call gradients. Once we have the gradients, we enter a communication phase where the workers exchange the gradients with one another to agree on a global parameter update. And so once this is done, all the workers update the parameters according to the global parameter update, and we're ready to continue to the next mini batch. And this process continues again and again until the model converges. Data parallelism is simple and scalable, which makes it very popular. And it's also relatively straightforward to overlap between the computation and communication. When we compute the gradients for one layer, we start synchronizing the gradients for another layer. But data parallelism does have some challenges as well. where the first one is that we just require to fit a full copy of the model on each one of the workers. And if the model is large enough, it might not fit on the worker's memory. So that was a motivation for us to pack TRN1 with a lot of memory. Another challenge with data parallelism is what we refer to as weak versus strong scaling. It's relatively straightforward to scale out with data parallelism if we're willing to grow the mini batch together with the number of workers. Think about training with 2 workers in a batch of 64, or training with 4 workers in a batch of 128. In both cases, we're training with a batch of 32 per worker. And that means that each worker is relatively utilized to the same level in both examples. This is called weak scaling because we grow the problem size, in our case the mini batch size, together with the number of workers. And the problem with weak scaling is that as we grow the mini batch size, we typically need to do more work or more training steps in order for the model to converge. And that means that training will take longer. Strong scaling, on the other hand, means that we can add more workers without increasing the mini batch size, and thus training will complete faster. And to enable strong scaling, we had to make sure that Trainium is efficient across a variety of batch sizes, including small batches. For cases that data parallelism, that the model doesn't fit in the worker's memory, we typically use some form of model parallelism. And one quick note here, there are interesting techniques to combine data parallelism with weight sharding, but we're not going to cover them today. Model parallelism can further be split to a set of sub-techniques, with the first one being pipeline parallelism. And pipeline parallelism, also called interlayer model parallelism, is relatively straightforward. Each worker gets assigned with a set of layers, and we form a pipeline of execution between the workers, just as the name suggests. So here, for example, we take layers 1 and 2 and assign them to worker 0, layer 3 to worker 1, and layer 4 to worker 2. In this case, we don't split the training data set, but rather all workers process the entire data set in a pipeline manner, just like you see on the screen right now. So just to compare and contrast with data parallelism, we sharded the training data set across the different workers. And here with the model parallelism, and specifically pipeline parallelism, we shard the model across the different workers. Pipeline parallelism can fit much larger models. We no longer need to fit a full copy of the model on each one of the workers, but instead we only need to fit one layer or a few layers on each worker. So this can enable naturally enable fitting much larger models. And pipeline parallelism also has a relatively simple point-to-point communication pattern, which puts less burden on the interconnect. And as for the challenges, we still need to fit at least one layer on each worker. And if a model has huge layers, it might run into problems with pipeline parallelism, which again motivated us to have a large memory in TRN1. And another challenge with pipeline parallelism is called pipeline idleness. If you think about the first worker in the pipeline, it needs to wait for all other workers to complete the forward pass calculation and then the backward pass calculation before it can do the backward pass calculation for its layers. And you can visually see the large pipeline bubble that we have here. Worker 0 completes the forward pass calculation and then waits for a long time until it can perform the backward pass calculation. In order to deal with pipeline parallelism, we typically employ a technique that is called micro-batching. With micro-batching, we do back-to-back calculations that are independent of one another in an attempt to hide the pipeline bubbles. Here you can see that I used 3 back-to-back micro-batches, and you can visually see how there's much less pipeline idleness with this execution. But one challenge that we have with the micro-batching is that now we want to overlap computation and communication, because we want to do the communication for the first micro-batch while already starting to perform the computation for the second micro-batch. So the takeaway for Trainium was that we wanted to make sure that we can overlap computation and communication. All right, next, let's talk about the second form of model parallelism, which we call tensor parallelism. And this is sometimes also called intra-layer model parallelism. And the reason is that we now split each and every layer between the different workers. This is both the big advantage and the big disadvantage of tensor parallelism. On the positive side, we can now fit big models and big layers. So we no longer have the problem of pipeline parallelism, where we needed to fit at least one layer on a worker's memory. Now, even if we have a huge layer, we can support that because we can split that layer across many workers. But on the negative side, this leads to all-to-all communication pattern after each and every layer, which puts a lot of burden on the interconnect. All right, let's see how this looks like. Here we partition each layer to different workers. And then the training data set is now sent to all the workers because they need to jointly perform the computation for the first layer. And now, after each layer is done, remember that each worker only performs a part of the layer computation. It doesn't have the full result of that layer, so we need to enter an all-to-all communication phase in order to assemble the full result of that layer, and then we can progress to the next layer. So pipeline parallelism can fit huge models and huge layers, which was the problem with the previous techniques that we discussed. And it's also quite efficient in reducing the mini batch size because multiple workers jointly work on the same calculation. And as for the challenges, first, it requires all-to-all communication, which puts a lot of burden on the interconnect. And it's also relatively complex to overlap between the computation and communication, because we need to finish the communication for layer K before we can start the computation of layer K plus 1. And there are some techniques like micro-batching to help here as well, but in general, that's one of the challenges of tensor parallelism. The takeaways for TRN1 is that we need a high bandwidth and low latency interconnect, and that we, again, need to make sure that we can overlap computation and communication as much as possible. So let's recap. We talked about data parallelism, and we talked about model parallelism, and within model parallelism, we talked about two sub-techniques, pipeline and tensor parallelism. Now, it's important to note that these forms of parallelism or scale-out training are not mutually exclusive. In many cases, we use a combination or maybe even all three of them in order to scale a very large model. You can see an illustration on the right. And as we covered the different forms of parallelism, we also assembled a list of requirements for TRN1 so it can be as efficient as possible for scale-out training. We noted the need for large accelerator memory so that we can fit large models and large layers. So we packed 512 gigabytes of HBM2E accelerator memory into TRN1. And this is the instance with the most accelerator memory that we have. Next, we talk about the need to have a high bandwidth, low latency interconnect. So we packed TRN1 with a massive 768 gigabyte per second of an inter-chip interconnect, which we call NeuronLink. And the NeuronLink interconnect also comes with very low latency of about 1 to 2 microseconds. For communication between servers, we offer TRN1 Ultra clusters that you heard of before, which deliver petabit scale of non-blocking EFA networking across more than 10,000 Trainium devices. Each TRN1 server has 800 gigabit per second of EFA networking with around 10 microseconds of one-way MPI latency. We also talked about being efficient at small batch sizes in order to enable strong scaling. Here you can see the relative performance of TRN1 and P4D across different batch sizes when training BERT large. And what you can see is that TRN1 maintains high performance even at low batch sizes. And again, this will enable stronger scaling. And stronger scaling means that we do less work in order for the training to converge, which in turn leads to faster training time. And lastly, we talk about overlapping computation and communication. We could have built Trainium with the same engines to handle both the core machine learning computation and the collective computation, which is the communication part. But this would have led to serialization, just like you see on the timeline on the screen. So instead, just like you heard in the beginning, we have dedicated engines for collective compute, which allows us to overlap computation and communication as much as possible and get to this dense timeline that you see here on the screen. All right, so with all of this, this is how we ended up with the TRN1 spec that Chetan showed you before. And I hope that with this journey that we kind of just went through together, you understand the meaning and reasons behind all of these decisions that we've made, and you understand why you're so excited about TRN1. But before we wrap up, all these great hardware features need a software that is easy to use and caters to a wide range of applications and use cases. And that's exactly why we built the Neuron SDK when we launched Inferentia, our inference accelerator. So now we're extending the Neuron SDK to support training as well. Neuron has a compiler and a runtime, and it extends all popular machine learning frameworks in order to natively support training, just like it did for Inferentia. And on top of that, we also added new capabilities that are dedicated for training, including just-in-time compilation, distributed training support, and eager execution. We put a lot of effort to make sure that Trainium is very easy to use. One of the examples that we use in order to do that is that we download the models as is and make sure that they can run on Trainium at high performance. So here, for example, we downloaded a Hugging Face BERT model, and just with a few lines of code, we train it on Trainium and at high performance. So this point is very important. We don't require any model changes or operator tweaking or data type conversion. Just bring the model as is, and Neuron will run it, and will run it at high performance. All right, let's wrap up. TRN1 enables the most cost-efficient training in the cloud for a wide range of deep learning workloads. AWS is innovating across chips, servers, and data center connectivity in order to provide our users with access to cutting-edge hardware at scale and on demand. And we're optimizing for maximum developer efficiency with the Neuron SDK and with integration to popular machine learning frameworks like PyTorch and TensorFlow, as well as integration into AWS services like SageMaker, ECS, and Parallel Cluster. We're super excited about TRN1. We think it will be a real game changer here. We're hoping that you're excited as well. And again, thanks very much for being with us today, and we'll hang out here for questions.